Here we go. So, geometric growth and decay. So, basically, this is all word problems, this whole lesson. I know. Everybody's excited.
Always been doing word problems?
Yes. Every math question is a word problem, essentially, because they all involve words. I know.
What's the difference? We can just skip this unit.
Okay. All right. So, when I went to UVic, they had a rabbit population. All right. They were, yes, but they were everywhere on the grounds. If you walked up there was rabbits just everywhere. Like you walk up and you could pet them. There were so many. They were so used to human contact. They were covered the grass everywhere. And then they magically disappeared. They went to a big field somewhere. Right? I may or may not have known somebody that made rabbit stew. All right. I know somebody that did. Why did they what? Because there was I don't know. They were just getting into everything. There was thousands of them. Like literally you couldn't walk across a field. There were so many rabbits. You think you have a rabbit population here? No.
Just kicked one over the field.
Like it was insane. But I don't know why they made them go away. I was not privy to those discussions. So okay, so in 2010, how many rabbits were there? 1,500 rabbits. In 2011, they were growing at a rate of, what rate are they growing at? 20% per year. So in 2011, they had 1,800, 2012. So there's the rate of increase, 20% per year. Those are the numbers. So we're going to assume this is geometric because this is the unit we're doing in. So we assume everything's geometric. What is the common ratio? R. How do you find the common ratio? 18 over 1,500 is 1.2. Or, I know. Or, if you remember the logs unit? Remember this formula? Remember that formula? 1 plus or minus the percentage. The percentage is 20. 1 plus 20% is 1.2. All right. We're going to call this T1. What am I asking for? Which term? So if T1 is the number of rabbits in 2010, what is the term number that represents 2025? Everybody thinks 15?
Yeah. I don't think I feel like that makes sense. Yeah.
All right, let's check it. Here we go. You ready? 2010, 2011.
2016. Oh, 16, sorry. That's 16.
T1 is 2010, right?
Yeah, the 16th.
T2, T3, all the way up. But look at the number. We start at 0 here at the end. So T2 is T1. So when I get to 2025, what T is it? It's term 16. Okay, so just be careful when you're doing these questions which term number you're actually trying to figure out. Okay? All right, if the population continues to grow at this rate, what is the rabbit population, or estimate the rabbit population at UVic in January of 2025? What term are we finding? T16. What's my A value? 1,500, term 1. What's the rate of increase, the R value? To the power of 16 minus 1. Please tell me how many rabbits there should be in 16 years' time, or 4 years from now if they didn't call the rabbit, made the rabbits go away. 23,110.5. I'm gonna put a dollar sign, but that's not right. That's a lot of rabbits.
23,000 and a half?
Yeah, they had a half rabbit.
What is that? I roasted the half.
What?
I roasted the half.
Can you show us the picture?
Yeah.
All
It's like a double.
right. So 23,000 rabbits. All right. May I flip the page? Okay. Next page. Here we go. Vinnie. Vinnie borrows $10,000 from his parents to buy a car. That's a mistake.
Parents aren't getting it back.
I know. Why would you? No. His parents lend him the money interest free as long as he makes a payment at the end of each year. They agree to a repayment scheme where he owes 10% less at the end of a particular year than at the beginning of that year. This lasts for 8 years. At the end of 8 years, he makes what? Okay, whatever. All right. So, after 1 year, how much money does he owe? No. He's lent 10,000. End of year 1. After year 1, how much does he owe? How much? At the end of year 1, he owns $9,000 because he pays 10% every year, right?
Yeah, but does it go for 8 years?
So 10%. What's 10% times 10,000? 1,000. So he pays 1,000 off. So he owes $9,000. Correct? Yeah. Are we okay?
If it lasts for 8 years, it's not going to pay the extra 2K. Where's that going?
He makes one final payment. See. All right.
Yeah.
All right. So essentially, how much is the loan decreasing every year? Okay, 10% of that is true. What am I trying to say here?
0.1.
What am I? How much of the previous year's money is left?
90%.
90%. Two people said that, right? So remember this from
You plus minus the percentage, guys.
see that one, right? So you're essentially going 10,000 times 0.9, correct?
No.
That's how I got 9,000.
Exponent, man.
No, I'm talking about the first one.
Okay, but like the second
All right.
one.
So the R value is 0.9. This is also called the geometric growth factor if we were in whatever. We're just going to leave it. R value is 0.9. All right. How much is he going to owe at the end of the 7th year?
In my opinion,
Okay.
3,625.
So you would be wrong. Okay. So this is the beginning of the sequence. There's T1. After 1 year, he owes 9,000. That's our A value. After 2 years, what's he going to owe?
808,000.
There you go. You're going to multiply by 0.9 again, right? That's essentially what we're doing here. So we know that our A value is 9,000.
Not at this rate. Not if you have 90%.
Our R value is 0.9. I want to know how much he owes at the end of the 7th year. So what's my N?
7.
It's 7.
Oh, so A value is 9,000. It's not 10.
Yeah, because it's at the end of the year. How much does he owe? It's not how much he was lent. But there.
You can do 10,000 and don't do 7 minus 1.
Yeah.
Why are you teaching?
You're killing me, Dante. All right. So T7 is going to be A R to the 7 minus 1. So how much does he owe at the end of the 7th year? 4,782.
What did I say? Now, singing, what did I say?
3,600.
Yeah. Thank you for remembering that. You did not say that number. All right, so after 7 years. Now, Dante is correct. Stole all my thunder.
What did you say?
All right. So, what you can do, and we're going to get to this at the end of the next page or the next 2 pages, is that doesn't seem to totally make sense. Like it does when you write it out, but starting with how much this value is initially doesn't totally make sense. I'm going to show you how to generate the formula. I'll show you the formula right now, but how to actually get the formula, Dante. You can literally just go T7 is equal to 10,000.9 to the 7. Okay? So what we're doing in this one, and I'm going to show you how you get this and when to use this, is you're actually using the initial amount that you were lent and then the number of years that you have the loan. Okay? Sorry? You can't call it term 0 though, because then you get a negative exponent and it all goes crazy. But it's essentially that in a non-mathematical way. All right? All right. Okay, so tell me, here's some practice. What is the R value if I give you this information? So this is right back to the logs unit. If I say the rate of inflation is increasing at 3.5% each year, what is my R value?
Inflation doesn't exist. 35.
If we have
0.65.
Guys, you have to take 1 plus minus 3.5%.
0.9.
How can you do 0 if there is none?
1.035. You have to have the 1 plus or minus.
1 plus minus
Right? If you're going up 3.5% per year, you're multiplying by 1.035%. All right? All right. Number of fish in a lake is decreasing by 2% per year. What is that?
How can you decrease if some fish are burning? Burning.
Burning. 0.98, right? It's 1 plus or minus the percentage. The number of rabbits in a population is doubling each year.
2.
There you go. 2. The value of a computer decreases by 1/5.
1 plus minus the percentage.
We didn't do that on the last one, Dante. Why are we doing
It's 4/5, or for those of you, 0.8.
Mr. Baldwin, why did we do that for C?
Because I said it's doubling. I didn't give a percentage.
Is that the percentage? Is it percentage?
You can make it a percentage, 0.2.
Can I make it a percentage?
No.
No, it's 230.
You could say 200%. Yeah, you could say that, but the ball rebounds to 3/4 of its previous height.
3/4.
It's 3/4.
Yeah. Wow, I'm so good. Because it's
Or 0.75.
I'm so good. This doesn't. I don't understand.
It's bouncing up to 3/4 of its previous height. So is it getting taller or is it getting less?
It's like
It's getting less, right? So it's going to be 75% of the previous height. That's what you got to do. All right? But you're getting less. So it'd be 1 minus.
Sure.
It's going to no, because it says it's going to 3/4 of the previous height. So it's this word of means multiply, right? Value can decrease. Computer decreases by 1/5.
No.
So it's 4/5 of.
It doesn't look like that.
Well, we can go over.
All right. This is a famous problem that you will see on your test. All right.
This thing sucks.
A rubber ball is dropped from the top of a building. All right. This was on old provincials. This is like on everything. 20-meter high building. Each time the ball bounces, it bounces back up to 80% of its previous height. Calculate to the nearest centimeter the height of the ball after the 15th bounce. Okay. My advice is to sketch it out. Not all the bounces, but just the first few, just so you get an idea of what's going on. You don't have to. I'm not going to give you marks if you sketch it out, but I'm going to sketch it out. So we are at the top of a little building that is 20 meters high. We throw the ball off. Let's do it in a different color. Exactly. We're ignoring friction. We're ignoring gravity. Well, I guess we're taking into account gravity because it only goes up to 80%, but whatever. There's our bounces. Okay? Dot, 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 dot. All right. This is the bounce. Bounce 1 right there, right? How high does it bounce up to after bounce 1? 80% of what? Which is 16. So this is 16 meters high. And then it's 80% of 80% of 80% of 80% all the way down the line. Okay. All right.
Oh, because the first bounce is.
All right. Why does T15, if we use T1 is 20, so I'm saying T1 is 20, why does T15 not give me the answer to the problem?
Because it's at the end of the bounce.
So if I'm calling this T1, the initial height, okay, after the first bounce, I get T2, right? So after bounce 2, I get T3. After bounce 3, I get T4. So after bounce what, I get T15. After bounce 14. So T15 would be bounce 14. So what do you actually need? You would need T16, right? So if first bounce, equals T2, then 15th bounce equals T16. All right, let's solve the problem. So I want to know how high it bounces after the 15th bounce. So I'm looking for T16. Oh, you can. I'm going to show you how else you can do it. It's another way to do it. But this is Lucasitos. Lucasitos? Lucasitos? I don't know how to say that name. This guy's name. All right. So we go T16 is equal to, what's my A value? What's the initial height?
20 meters.
20, because we're using T1 as 20. What's the R value? What's the R value? 0.8, right? It goes to 80% of the previous height.
Lucasito is Spain. It's Spanish.
What?
Lucasito. It's Spanish.
Okay. Thank you. 60 minus 1. So how high is it? 0.704 meters. Nice, let's put meters. All right. Nicoletta disagrees. She thinks T15 should be the answer to the problem. How do we make it so that T15 is the answer to the problem? T1 is 16. So if you do this, that's 20. It bounces, boom. That's T1, which would be 16 because this is the bounce. Bounce 1, T1 is equal to 16. And then you can all the way down. So her formula is going to be, I'll write the general. A value is going to be 16. R is still 0.8. And then if you do that for T15, 14, you should get the same answer, 0.704 meters. If you don't, then we've done something wrong, but you do. Okay, so you have choices in these questions of how you want to solve them. Do you want to start with the A value as the initial height, or do you want to start with it after the first bounce?
You're asking centimeters. You said meters.
Is it as for centimeters? It did. Ah, well, we're not doing that. We're leaving it as meters. I'm going to make the assumption that you can convert.
Skip question like that.
I can.
I do the test.
No, you have to do what I say on the test.
Will you say that on the test?
I'm telling you right now, blanket statement. You have to do what I say on the test.
No, but like,
I'm not going to ask you to convert centimeters to meters or meters to centimeters.
you said 100.
I know.
I have to be the model.
All right. We've already done that one. Okay. So, for each student, write an equation. I only wanted. Let's do for Lucasto. For Luke. All right. Write an equation which represents the height of the ball after X bounces. So the sort of easier, more intuitive way to think about this is how many bounces and just plug that number in. Okay? So if we look at this, where's Luke's question? I want to use the initial height and the number of bounces to get our value of how high it bounces. So I know our A value has to be 20. So Tn is going to be 20. We know that R value is 0.8. That doesn't change. Because I'm telling you it's 80% of that height. And then I say that is n, and I say n is the number of bounces. Okay. I don't have to do n minus 1. I can just do n, where n is the bounce. Okay? Because that takes into account the fact that T2 is your second, or T1 is the initial, not the second. Okay? And I'll write a formula here in a sec that kind of summarizes that. So, another question based around this is, how long before it's less than 2 centimeters high? It bounces up to less than 2 centimeters. Why are they converting? Whatever. Okay. So here's our question. We want to solve this. I want to know, when is it 2?
You gotta change it up to
Just changed it.
Man, you're saying centimeters or meters? Oh, really?
I'm saying meters.
Okay.
That's a very good.
Because it's the way they actually solved it. They say centimeters, but they actually solved it with meters. So, all right. So, less than 2 meters. When will the bounce be less than 2 meters? Which bounce will that be? Okay. So we put 2 in for our Tn. And we solve for? Let's solve for log. We solve for our exponent, which because is the unknown, we have to use log. So what's the first step here? Divide by 20. Now what do you do? Which log do you want to use?
Natural, but write it weird.
Log 0.1
Wow.
equals n log 0.8. Divide by log 0.8. So on your calculator, please go log 0.1 divided by log 0.8 and tell me what n is. Please.
I love you. 10.3.
10.3. People get that? Okay. So if it takes 10.3 bounces, I know 0.3 doesn't really make sense, but we'll just go with it. 10.3 bounces to bounce to 2, because that's what we solved. When is it 2 meters? When will it be less than 2 meters? Which bounce?
11.
The 11th bounce, right? You have to bounce one more. After 10 bounces, or 10.3 bounces, it bounces up to 2. So it's the next bounce, it'll be less than 2. Okay? Bounces to be less than 2 meters. Do you want me to stop there? I think I need to stop there. All right. Okay. Hang on.